You settle into the quiet of the moment, letting your breath soften as though it is remembering its natural rhythm. You do not force it, you simply notice the way it rises, the way it falls, like a small tide inside your chest. Around you, the room settles too, as if it is waiting for you to slow down enough to hear something long overlooked. You sense, faintly at first, that beneath the everyday sounds lies a softer world, a world so delicate that it almost escapes attention. It is the whisper beneath reality, the subtle motion of atoms that never quite rest. This is where your journey begins. You close your eyes, not to shut things out, but to listen more deeply. In the darkness, you imagine tiny vibrations weaving through every surface. The chair beneath you, the air around you, even your own skin, each is alive with motion so small it dissolves into stillness. Yet that stillness is only your perception. Underneath it, atoms tremble with quiet energy. Their motion is gentle but unceasing, like the trembling of a spider's web touched by a drifting breeze. You breathe into this thought, letting its simplicity comfort you. Nothing is truly still, and yet the world holds together in calm. You travel inward, through the familiar layers of your senses, until you reach the threshold where ordinary experience grows thin. Here, the hum of atomic life becomes almost audible in your imagination, a faint shimmering, a soft rustling, a quiver of being. It feels less like a sound and more like an awareness that everything around you participates in a quiet dance. Quantum sensing begins in this hidden place. It begins with listening to the world without disturbing it, with noticing what is already happening instead of pressing it to reveal itself. As you rest with this awareness, you picture a single atom, suspended in space. Though impossibly small, it vibrates with a rhythm all its own. Its electrons shift in blurred orbits, cloud-like and uncertain. It moves not because it wishes to, but because movement is woven into its existence. You imagine leaning closer, closer than any ordinary instrument can reach until the faintest tremble becomes clear. A quantum sensor performs a gesture like this. It listens for the whisper of an atom without pushing it, without overwhelming its subtlety. This gentleness is what makes quantum sensing extraordinary. You drift deeper into the idea, following the motion of countless atoms. You imagine them beneath your feet, arranged in the floor. You picture them in the air, linking and parting like dancers forming patterns too intricate to follow. You imagine them inside your own body, contributing to every breath, every heartbeat, every silence between beats. Even in perfect stillness, you sense a world of perpetual movement. And in this movement lies information so faint that only the most delicate instruments can gather it. Quantum sensors capture the tiniest shifts in this motion. They detect changes in energy, magnetic fields, or vibrations that classical tools are too blunt to perceive. You imagine a string drawn so tight that the slightest breeze makes it sing. A quantum sensor listens for that breeze. It listens for disturbances so gentle they would pass unnoticed in the noise of ordinary life. The sensitivity is breathtaking, but its source is softness, not strength. You rest in that thought, that listening deeply can reveal more than straining. You feel your breath again, rising and falling like a calm tide. With each inhale, you imagine drawing closer to the unseen world. With each exhale, you settle more comfortably into it. You picture atoms vibrating not randomly, but with patterns shaped by temperature, pressure, or fields too subtle to name. These patterns ripple outward, touching everything. You sense how quantum sensors trace these ripples, sketching a map of the unseen. Your body relaxes as you realize that even the hidden world has order, texture, story. You reflect on how scientists learn to hear such small whispers. They built tools that harness quantum properties, the strange, beautiful rules that govern particles at their smallest. These tools can detect shifts in energy as slight as the movement of a single atom. They can measure fields so faint they seem like imagination. They can listen to vibrations that reveal the presence of something far away. And they do this not by overpowering the world, but by joining it quietly. As you breathe, you feel yourself mirrored in the softness of the sensing. Your attention becomes a kind of sensor too gentle, curious, unhurried. You sense your thoughts drifting like small particles in a warm current. You notice how they appear, shimmer, and pass away. You do not need to hold them. You simply observe them, the way a quantum sensor observes its delicate world. The more lightly you pay attention, the more clearly each thought reveals itself. Slowly, you imagine the entire world as a tapestry of vibrations. Mountains hum with the shifting of atoms in their stone. Oceans whisper with the jostling of water molecules. Your own breath creates tiny waves in the air, sending ripples into the space around you. You are part of this tapestry, woven into the same pattern of motion. Quantum sensing is simply a way of noticing what has always been there. It is a reminder that quietness is full of life. You drift in this idea, letting it cradle you. Even silence, you realize, is crowded with motion. Even emptiness is filled with subtle rhythms. The universe is never still, and neither are you. Your body moves with the pulse of your heart, the flow of your breath, the hum of your cells. And beneath those motions, the atoms themselves restlessly shimmer. You are built from whispers, from movements too small to see, from energy endlessly circulating through the world. As you rest in this thought, a gentle curiosity rises. If everything vibrates, if everything whispers beneath the surface, then what other secrets might be hidden in this smallness? What else might be waiting for someone patient enough to listen? You linger here longer, sensing the depths within each trembling atom, feeling an invitation drawing you onward. You enter this chapter the way you might step into a dimly lit room at night, guided not by clarity, but by trust. The familiar tools of your daily world, rulers, clocks, balances, all the objects built to capture certainty, seem to fall away behind you. You sense their limitations as gently as you sense your own exhale, noticing that they are built for the large, the loud, the obvious. But here, in the quiet domain of the very small, measurement requires a different kind of touch. It demands softness instead of pressure, attention instead of insistence, patience instead of certainty. You feel yourself settling into that shift, as though the world is preparing you for a new kind of listening. You imagine reaching toward an atom the way you might reach toward a delicate soap bubble. If you prod too strongly, the bubble bursts. If you press too firmly, the atom's behavior changes, and the thing you hope to measure dissolves into something else. Quantum sensing was born from this fragility. It emerged from the realization that the smallest things cannot be forced to reveal themselves. They must be observed without disturbance, touched without touching, known without being pinned down. This subtlety relaxes you. It reminds you that understanding does not always require control. Sometimes, it simply requires presence. You picture an atom drifting in darkness, suspended like a tiny lantern of probability. It is not fixed in place the way everyday objects are. Instead, it shimmers between possibilities, here and not here, moving and not moving, certain and uncertain. This shimmering is not an inconvenience to scientists, it is the source of quantum sensitivity. Because the atom is unsure, it reacts to forces too faint for certainty-bound instruments. You imagine these faint forces as ripples passing through a still pond at dusk, barely visible, but captured beautifully when the surface is calm. Your breath becomes that calm surface. As you inhale, you let the air settle into your body. As you exhale, you release the need to define things sharply. Quantum measurement is never about pinning reality down. It is about sensing the way probabilities shift, the way possibilities lean, the way a faint influence nudges the outcome of a fragile system. You imagine watching this with quiet fascination, not expecting precision in the classical sense, but sensing meaning in the pattern of uncertainty. You drift deeper into this idea, noticing how your mind softens around the abstract. The unmeasurable becomes less intimidating as you spend time with it. You imagine a tiny magnetic field brushing past an electron, altering its orientation by the faintest angle. A quantum sensor might detect this angle by noticing how the electron's alignment changes the way it interacts with a beam of light. It is less like reading a number from a machine and more like noticing a whisper change the tone of a room. As you picture this, you feel your own senses becoming attuned to subtler cues, the sensation of air on your skin, the quiet rhythm of your heartbeat, the gentle sway of thoughts rising and fading. In the classical world, measurement is about certainty. In the quantum world, measurement is about story. Each observation is a narrative written in probabilities, revealed through the shifting of patterns. You imagine these patterns as faint constellations scattered across a night sky. You cannot grasp them directly, but you can watch the way they gleam, the way they drift, the way they hint at something beneath the surface. A quantum sensor reads this sky by letting the patterns speak for themselves. This realization brings a sense of peace. You feel the weight of needing exact answers lift from your shoulders. Quantum measurement teaches you that uncertainty is not a flaw, it is a landscape. It is a terrain where gentle forces leave delicate footprints, where the smallest influences become visible only because the rules of the tiny world are so different from the rules you know. You rest in that difference, letting it quiet the part of your mind that yearns for everything to be defined. You picture a cloud of atoms cooled almost to absolute stillness, hovering in a trap of magnetic fields. Because they are so calm, so nearly motionless, the slightest disturbance becomes noticeable. A passing vibration. A change in gravity's pull. A whisper of electric field. These atoms respond with minute shifts, like tall grass swaying under the lightest breeze. A quantum sensor watches that swaying, translating it into knowledge. You imagine standing in a field of this grass, feeling every subtle movement around you. Nothing pushes, nothing demands. You simply notice, and noticing becomes measurement. You sense how quantum measurement mirrors your own inner life. Thoughts drift unpredictably, appearing and fading like particles shifting among possibilities. Emotions rise in gentle waves, influenced by forces so subtle you cannot always name them. Yet you can observe these shifts without interference. You can watch your inner probabilities rearrange themselves. Like a quantum sensor, you can sense the unmeasurable. You can feel the story beneath the noise. This connection brings you deeper into the calm of the chapter. You imagine moving through the small-scale world like a traveler in a misty forest. The trees are shapes more than forms, the path is suggestion more than line, and yet you feel safe because you trust the subtle cues guiding you. A faint glow, a soft shift in the air, a rhythm of movement. Quantum sensors move through this mist with similar trust. They do not need certainty. They need only the quiet space where possibilities define themselves. As you rest here, an emerging question gently touches your awareness. If quantum sensors listen to the patterns that form from uncertainty, what else might be possible if particles could exist in more than one state at once? What if sensors could use that softness, that multi-layered existence, to feel even deeper into the unseen? You feel this question settle beside you, not demanding an answer, but inviting you forward. For now, you remain in the soft quiet of this chapter, feeling the comfort of measuring without grasping, knowing without force. But just ahead, in the unfolding stillness, you sense another truth approaching, one where particles do not choose a single state until observed, where possibilities overlap like the layers of a dream. And as you lean toward that mysterious threshold, you feel yourself drifting gently into the next chapter's waiting dance. You enter this chapter the way you might slip into warm water at twilight, letting the surface close softly around your shoulders. The world grows quiet as you settle in, the familiar edges softening until they begin to blur. It is in this blurring that the next part of your journey begins. Here, the rules rules about how things should behave, where they should be, what they should become, start to loosen. You feel a gentle spaciousness around you, an openness that invites you to breathe more slowly. This is the realm of superposition, where particles are not confined to a single identity but drift among several possibilities at once. You imagine yourself floating beside a tiny particle, an electron, perhaps resting in a dim, quiet space. Instead of occupying one precise spot, it seems to shimmer across a small region, as though it is considering multiple positions at the same time. You sense not indecision, but freedom. The electron is not scattered, it is simply more than one thing at once. This layered existence feels surprisingly comforting, like hearing two harmonizing notes in a song. They occupy different tones, but together they form something whole. As you breathe, you notice how your mind softens around the concept. You may have been taught that things must choose, left or right, here or there, up or down. But this tiny particle shows you otherwise. In the quantum world, possibility is not divided, it is woven. A particle can be in several states, each one gently overlapping with the others. These overlapping states are not competing, they coexist until something in the world asks the particle to decide. Until then, it simply dances among them. You picture this dance as a slow drift through morning mist. Shapes appear and disappear, not sharply but softly, as if they are suggestions rather than declarations. You feel the way this imagery relaxes you, as though your own thoughts could be allowed to float without committing to one shape too soon. Superposition is like that, an invitation to rest in the openness of possibility. A quantum sensor uses that openness to detect forces too faint for ordinary instruments. By placing particles in these overlapping states, scientists create systems that are exquisitely sensitive to even the smallest nudges. This makes sense to you on a deeper level. When you hold yourself rigidly, trying to stay certain, it takes a great push to move you even a little. But when you relax, when you let yourself soften and open, a small influence can gently guide your thoughts or shift your feelings. Superposition is the quantum version of that softness. A particle held in a single, definite state resists small disturbances. But a particle drifting among many states, held lightly rather than tightly, responds to the faintest whisper of change. You imagine watching such a particle being prepared for measurement. A scientist shines a quiet beam of light, or applies a tiny magnetic field, coaxing the particle into its delicate overlapping pattern. In this state, it becomes like a perfectly still pond, ready to reveal even the gentlest ripple. You picture the ripples as faint waves moving across the particle's possibilities, altering the balance between its overlapping states. A quantum sensor reads these subtle waves, translating them into information about the world, a world too quiet or too delicate for conventional tools to detect. As you stay with this image, you begin to feel how superposition mirrors your own inner landscape. At any moment, you carry many versions of yourself, many thoughts, emotions, intentions resting together before you choose which one to express. You are not a single, fixed point. You are a field of possibility, shifting and shimmering gently within. This realization softens something inside you, easing the pressure to always know, always decide, always be defined. You feel yourself expanding, just slightly, into a more spacious self. You drift deeper into this space, imagining the electrons dance, becoming slower, more luminous. The overlapping states seem to glow with equal potential. One state might correspond to being in one location, another to being somewhere else, a third to spinning one way or another. In your mind, these states become like translucent layers of watercolor paint, each one adding depth and subtle color. None of them is fully chosen, but each contributes to the particle's whole being. You sense the quiet beauty of this layered existence. Quantum mechanics tells you that these states are not metaphorical, they are real. A particle in superposition genuinely holds multiple possibilities simultaneously. It is not that the particle hurriedly switches between them, it is that the particle occupies a broader, more nuanced existence than you can see. This truth brings with it a hint of wonder. If something so small can hold so many possibilities, how much more might be hidden in the layers of the world? How much might be hidden in the layers of yourself? Your breath grows slow, and even as you ponder this, you realize that superposition is, at its heart, an expression of potential. Not chaotic potential, not aimless drifting, but a calm readiness to become. The particle is waiting to be asked. Waiting for a measurement. Waiting for the world to interact with it in a way that draws one possibility into focus and allows the others to fade. This process is known as collapse, though the word sounds harsher than the reality. Collapse is more like a settling, a narrowing of attention, the way your mind chooses a thought among many drifting options. Quantum sensors rely on this process. They let the world influence which of the overlapping states becomes real. By observing how the final choice shifts in response to tiny forces, scientists learn about those forces. In this way, superposition becomes a tool, a subtle, powerful method of sensing change. You find a quiet satisfaction in this idea, that openness leads to insight, that gentleness leads to precision, that possibility leads to truth. You let this understanding drift through your awareness like a warm current. You feel how the world of the very small is not frantic or chaotic, but delicate and profound. The dance of superposition is a reminder that existence is not always singular, not always definitive, not always confined to one path. Sometimes, being more than one thing is the most natural expression of reality. As you float at the edge of this chapter, you sense another question rising, one woven into the gentle movement of overlapping possibilities. If particles can exist in many states at once, what happens when two particles become linked, sharing their states even across distance? What kind of dance emerges when their possibilities intertwine? You feel yourself drifting toward the deeper mystery, carried by the quiet motion of connection waiting just beyond the horizon. You rest inside a quiet room, and yet the world around you is trembling with a hum too small for your senses to touch. You breathe slowly, and in that breath, millions of molecules drift in and out, brushing against you with movements so gentle they hardly deserve the word motion, and yet every one of them holds a story. Tonight, you turn your attention toward the smallest motions of all, the trembling dance of atoms, the soft and constant breath of the universe that quantum sensors learn to feel. You may think of atoms as tiny, solid beads, but in truth the atom is mostly emptiness, a small, dense nucleus wrapped in a cloud of probability, where electrons do not orbit in neat circles but flicker like candlelight in a draught. Even when you lie perfectly still, each atom in your body moves with a faint, persistent pulse. This subtle motion is called quantum vibration, and it never quite stops, not even in the coldest depths of space. It is the universe whispering to itself through motion. As you settle deeper, imagine your body as a cathedral of atoms, each one humming at its own frequency. The atoms in your bones vibrate differently from those in your breath. The atoms in the air vibrate differently from those in the earth beneath your feet. And in this vast choir of motions, quantum sensors act like exquisitely trained ears, able to listen to vibrations so faint that they vanish beneath ordinary instruments. They do not simply measure what is loud, they measure what is nearly silent. What makes these vibrations so quiet is the scale at which they happen. When you touch a table with your hand, the movement you feel comes from billions upon billions of atoms acting together. But the motion of a single atom is so soft that even the smallest breeze of background noise can drown it. A passing truck, a shifting floorboard, even the warmth of your own body. Quantum sensors use special tricks to strip away these intrusions, allowing them to hear only the subtle music of the unseen. The first trick is cooling. Not cooling in the ordinary sense of a winter wind, but cooling carried to astonishing extremes, temperatures a fraction of a degree above absolute zero. At these frosty depths, atoms slow their jitter just enough for their faint signals to stand out from the noise. You might imagine each atom curling into itself, as though hugging a small pocket of stillness. The colder the atom, the more clearly it can be heard. Another trick is trapping. Quantum sensors often hold atoms in place with beams of light so gentle they do not crush or burn but cradle the particles in invisible hands. These light traps are called optical lattices, delicate cages made of intersecting laser beams. Inside such a lattice, atoms float in perfect alignment, like fireflies held in a crystalline web. When they vibrate, they do so in unison, forming a chorus instead of a chaotic crowd. This harmony makes their tiny tremors easier to measure. Lying here now, you might picture these light-woven cages as a forest of frozen stars, each point holding a single atom glowing softly in the dark. The forest stretches outward, lattice after lattice, forming a landscape made not of trees but of pure motion, pure potential. Physicists look at this landscape with awe, listening for changes in rhythm. A slight shift in vibration might signal a passing wave of gravity. A slight wobble might reveal the presence of a particle that has never been seen before. The most remarkable part of these sensors is not the light or the cold, but the coherence, the way quantum states align when treated with perfect care. A coherent quantum system is like a row of pendulums swinging in time with one another. Push one pendulum too hard, or let a gust of air disrupt it, and the rhythm dissolves. But when the pendulums remain aligned, their shared motion grows stronger, easier to detect. Quantum sensors rely on such synchronized motion to read the universe. Your own mind can feel coherence when your thoughts begin to line up, when your breathing and heartbeat fall into rhythm. In the same way, atoms held in coherence reveal signals that would otherwise be lost. Coherence gives shape to the whisper. Coherence gives strength to the unseen. These vibrations are not only about motion. They also hold energy. In quantum mechanics, the energy of a vibrating atom is not a continuous wave but a series of distinct steps, like rungs on a ladder. It can occupy one rung or another, but not the space in between. This quantization is what gives quantum sensing its name. Sensors measure changes in these discrete jumps of energy, tiny shifts in frequency that reveal conditions around the atom. For example, a magnetic field nudges the electrons around an atom, changing the rhythm of their vibration. A gravitational shift tugs on the nucleus, altering its energy slightly. Even small fluctuations in temperature change the atomic dance. Quantum sensors listen to these shifts the way a musician listens to the tuning of a violin, hearing tension, pressure, and vibration all through the quality of sound. As you breathe, imagine those vibrations settling into your awareness. Your inhale collects energy. Your exhale releases it. You sense the warmth of your own body as a field of motion. If you were a quantum sensor, you could detect the faint rise and fall of temperature in your fingertips, the drift of magnetic lines between your bones and the Earth, and the tiny gravitational waves that pass through you from distant cosmic events. Quantum sensors bring us nearer to these unseen forces by expanding the range of what can be measured. They detect motion so slight it is measured not in centimeters or micrometers but in quantum states. They can feel the presence of dark matter by watching atoms hesitate in their dancing. They can sense gravitational waves by observing how atoms drift in their traps. Even the faint pull of the moon on the ground beneath you can be measured through atomic motion. But for now, there is an easier truth to hold: everything, everywhere, breathes with vibration. Even stillness is full of motion. The floor beneath you vibrates. The air around you shivers. The atoms inside you pulse with a quiet regularity. And this constant motion does not disturb you, it holds you. It wraps you. It reminds you that you are part of the same trembling fabric as the world around you. In this way, quantum sensors do not just detect motion. They show us that motion never disappears. Stillness is an illusion created by our limited senses. Beneath silence is always a faint hum. Beneath stillness is always a soft sway. When you realize this, the world feels more alive, more connected, more continuous. You let your breath slow. You let your thoughts soften. You imagine the field of vibrations around you thinning into a fine mist, settling like dew. The atoms continue their dance, but you float above it, watching from a quiet distance. You do not need to measure the vibrations to feel their presence. You simply rest in the knowledge that your body is part of a vast, shimmering symmetry. And as you lie there, drifting softly towards sleep, another thought rises at the edge of your awareness, a question waiting to carry you deeper. If atoms can reveal the breath of the universe through their vibrations, what stories do they whisper through their spins, those tiny magnetic compasses hidden at their core? You settle deeper into stillness, and the quiet around you expands like a slow exhale. The vibration of atoms you explored before continues its subtle hum, but tonight, you drift beneath that hum, toward something even quieter, even more delicate: the soft, secret turning of spin. Spin is one of the most mysterious qualities of matter. It isn't spinning, not in the sense of a tiny top twirling in space, yet the metaphor helps you picture it: a gentle turning, an orientation, a direction that an atom chooses to hold at its center. When you imagine spin, imagine a compass needle so small it is buried inside the very heart of matter, pointing one way or another in an invisible field. You cannot touch it. You cannot see it. And yet it is there, guiding the atom's magnetic whisper. Every proton, every neutron, every electron possesses this spin. And as you lie here, breathing slowly, millions upon millions of these tiny compasses within your body quietly point, flip, align, and relax. You carry an entire forest of orientation inside you, a magnetic undercurrent woven into your cells. Spin is the beating heart of quantum sensing. Because spin reacts to the faintest magnetic fields, so faint they would vanish in the noise of any ordinary instrument, it becomes a gateway to the unseen world. Spin shifts when a magnetic field changes. It relaxes when the environment warms. It precesses, rotating like a lighthouse beam, revealing time and space through its movement. To feel spin, imagine a single electron inside an atom. Picture it wrapped in its haze of possibility, the shimmering cloud that defines its quantum state. Deep in that cloud, imagine the electron's spin tilting slightly upward or downward. This tilt is what scientists call up or down, but it isn't a literal direction so much as a choice between two ways of existing. In that choice lies information and exquisite sensitivity to the forces around it. Quantum sensors monitor spin by placing atoms inside carefully controlled environments. Some sensors use vapor cells, tiny glass chambers filled with drifting atoms like a faint fog. Others trap atoms individually, arranging them like beads along a line of light. But in all these places, the principle is the same: keep the spin quiet, protected, untouched except by the faintest of influences. If the spin changes, the sensor knows something has passed through. Your own brain relies on spin, even if indirectly. The magnetic resonance imaging, MRI, machines used in hospitals read the spins of hydrogen atoms in your body. They push those spins into alignment with a strong magnetic field, then gently disturb them with radio waves. When the spins relax, they release energy, whispering information about the tissues they inhabit. A picture of your inner body, made from pure magnetic resonance. Quantum sensors take this idea and refine it thousands of times, sometimes millions. They don't force spins with strong magnets; instead, they let spins sit in near-perfect stillness. They use lasers to coax the atoms gently, to ask questions in the softest of voices. A spin might precess a little faster if a magnetic field grows stronger. It might tilt if an electric field enters the room. It might shift its timing if a passing mass warps spacetime just enough. And so, by listening to the behavior of spins, quantum sensors can detect signals from realms that previously remained hidden. You breathe in, slow and even, imagining your own atoms settling like silt in water. Their spins float in stillness. Their internal magnets tilt softly, aligning with the Earth's magnetic field, a whisper of north and south written into every molecule. The field is faint, yet your atoms feel it effortlessly. If you could observe a single atomic spin, you would see it precessing like a tiny gyroscope. This precession is the basis of magnetic sensing. The frequency of that rotation changes depending on the magnetic environment. In the quantum world, such frequencies become clues, a way for sensors to interpret the invisible landscape. One of the most elegant instruments that use spin are optically pumped magnetometers. They bathe atoms in light, pushing their spins gently into alignment. Then they quietly watch as the spins wobble, listening for changes in rhythm. These devices can detect magnetic fields 1,000,000,000 times weaker than those produced by a refrigerator magnet, weak enough to read the electrical activity of the human heart or the fields generated by the firing of neurons deep inside the brain. In this way, quantum sensors bring us closer to the body, not through touch or sight, but through the magnetic signatures that life generates as it moves. Your heart's electrical currents ripple outward with each beat. Your thoughts create faint magnetic patterns as neurons send their signals. These patterns drift around you, soft and transient, and the right quantum sensor can hear them as clearly as you hear your own breath in the dark. Spin also allows sensors to explore the farthest edges of the universe. Experiments that search for dark matter use arrays of carefully aligned spins, waiting for the slightest tap from a particle passing unnoticed through space. If dark matter interacts even faintly with atomic spin, it could tilt the whole array in a pattern that reveals its presence. You may imagine this array as a garden of reeds standing in still water. If a breeze passes through, the reeds bow together, measurable in their motion. Spin behaves in much the same way, bending as fields shift. To detect dark matter, scientists watch these reeds for a ripple that has no earthly explanation. And still, spin holds more secrets. Beneath its orientation lies another layer, superposition, a state where spin can be simultaneously tilted in more than one direction. It is difficult to imagine. Your mind is trained to picture objects in definite states, but in the quantum world, spin can rest in a blend of up and down, a harmony of possibilities. This superposition makes sensors more sensitive, as though you could listen to multiple frequencies at once. Superposition is fragile, though. The slightest disturbance collapses it, forcing the spin to choose a direction. This fragility is why quantum sensors must isolate atoms so carefully. Every vibration, every photon of stray light, every thermal fluctuation risks breaking the stillness. As you rest now, imagine holding something delicate, a soap bubble, a thin glass ornament, a snowflake resting on your palm. Superposition is like that. It is breathtakingly beautiful, but only for those who can hold perfectly still. To operate a quantum sensor, scientists must create environments where spins float untouched, like tiny boats on a perfectly calm lake. Any disturbance sends waves across the surface. Any shift in the world around them produces a measurable ripple. Your breath slows further, matching the rhythm of an invisible lake settling into stillness. You can sense how delicate this calm must be, how extraordinary it is that we can protect and observe something so small. And yet, because we can, new doors open, doors to invisible forces, faint signals, subtle interactions that shape the world. Spin gives information form. Spin gives the invisible a voice. Spin holds the key to sensing the quietest parts of reality. And as you drift at the edge of sleep, you feel the quiet magnetism of your own body, the gentle alignment of atoms, the silent turning of interior compasses you never knew you carried. You sense, somehow, that spin is not the end of the story. There is another layer, a deeper quiet, a deeper sensitivity. If spin reveals magnetic secrets, then what might be revealed when we let atoms flow freely, drifting like a quantum cloud, guided not by traps but by gravity itself? You ease into a slower breath, and the space around you deepens. Darkness becomes gentle here, not an absence but a soft container for things too subtle to see. You feel yourself drifting through a landscape without edges, a place where your sense is quiet enough to notice what usually slips past the faint, intricate weavings of magnetic fields that surround you every moment of your life. Magnetism is everywhere. It runs through the earth, threading north to south like a quiet spine. It swirls within the sun, crackling through solar storms. It pulses inside your own body, carried by the electrical currents that help your heart beat and your brain think. Yet most of this magnetism is invisible to you, hidden in the dark, not because it is far away, but because it is too soft, too delicate, too constant to feel. Quantum sensors change that. They take you by the hand and lead you gently into these darkened spaces, inviting you to sense what was always there. They do this not by pushing harder or shining brighter, but by learning how to listen in the deepest quiet. Their sensitivity comes from stillness, from atoms held so gently that the faintest magnetic whisper can shift them. You picture a small cloud of atoms floating in a glass chamber. They drift like tiny lanterns, glowing faintly under a beam of soft light. Each atom carries a magnetic moment, a little compass pointing in its own direction. When a magnetic field touches them, even a field thousands of times smaller than what your body naturally produces, their compasses shift. Sometimes they wobble. Sometimes they tilt. Sometimes they simply slow or speed their quiet rhythm. Quantum sensors watch those motions. They watch without touching, without disturbing, like observing a feather falling from across a room. The atoms tell their story through their alignment, through the frequency of their spin, through the shape of their glow when illuminated with a laser. You rest deeper into this image, a cloud of gentle motion, responding to forces too faint for the ordinary world to perceive. In the darkness surrounding you, magnetic fields form a braided tapestry. They twist and stretch across the ground, through the soil and stone. They curl around wires and buildings, fluttering with every passing current. They ripple through your heart each time it pulses with electricity. They slip around your scalp as your neurons fire in coordinated patterns. These fields exist whether you notice them or not. They shape the migration of birds, the stability of satellites, the rhythm of navigation systems. they guide compasses in the hands of explorers. Yet much of this magnetic world remains hidden because the signals are too small, too slow, too overlapped to distinguish. Quantum magnetometers, built from the delicate spins of atoms, can sense these hidden currents. They are not like metal detectors or bulky instruments, they are quiet observers, able to hear magnetic whispers buried in noise. One kind, called optically pumped magnetometers, uses light to nudge atoms into alignment. A laser sweeps across them like a warm breeze, organizing their spins so they point the same way. Then the sensor waits. If a magnetic field enters, the atoms shift. The light they absorb changes. The rhythm of their spin slows or accelerates. By reading this, the sensor knows exactly how the field has changed. You imagine these sensors like little rooms of stillness, each holding atoms that act as watchful guardians. They stand in the darkness not to chase it away but to make its textures visible. They reveal the layers of magnetic life that move through the world. There are even sensors built from a special kind of diamond, one with imperfections called NV centers. Inside these diamonds, tiny voids trap electrons whose spins can respond to magnetic fields with remarkable clarity. These diamond sensors are small enough to watch magnetic changes within a single cell. They can map the fields of miniature currents, trace the electricity inside neurons, and track biological processes that once lay entirely beyond reach. You take a slow breath, imagining holding such a diamond in your palm. It would look like a simple crystal, cool and unremarkable, yet inside, it contains the ability to reveal magnetic forces 1,000,000 times weaker than the flicker of your own heartbeat. Its atoms stand like sentinels, absorbing the world's quiet magnetism and letting you see. Magnetic fields, you realize, are not static. They pulse, shift, nod and unknot themselves. When charged particles move in wires, in the sky, in living tissue, they leave trails of magnetism, like ripples on a lake. Quantum sensors can detect those ripples even when they are buried beneath noise. They can separate one signal from another. They can map the patterns of a heart in real time or follow the faint pathways of electricity in soil as water flows through it. This sensitivity is not a matter of amplification. It is a matter of calmness, creating a space so undisturbed that even the smallest field leaves a trace. And you feel that calmness now. You feel the way silence allows the subtle to appear. You notice how your own body softens into the space around you, the faint magnetic hum inside you becoming part of the room's fabric. You picture the Earth's magnetic field again, a blanket wrapping the planet. It shields you from cosmic rays, steadies the atmosphere, helps animals find their way across continents. This field is not uniform, it swells and dips, it twists through minerals in the crust, it pulses with the activity of molten iron far beneath your feet. Quantum sensors allow scientists to map these variations, revealing the Earth's internal motions and hidden structures with exquisite clarity. In the same way, atmospheric scientists use quantum magnetometers to study storms in the upper atmosphere, auroras shimmering with charged particles, waves of magnetism rippling from solar winds. These measurements help predict space weather, protecting satellites and communication networks. All of this, you realize, is made possible by listening in darkness. Magnetism itself is not dark. It simply exists beyond your senses, waiting to be felt through gentler means. The darkness you imagine now is the quiet of perception, the soft closing of outer noise so that inner subtlety can rise. Your mind drifts through the idea that every magnetic field, no matter how faint, is a kind of footprint, a signature of motion, of interaction, of life. Quantum sensors read these footprints the way a tracker reads patterns in sand. And as you rest here, you begin to wonder what else lies in this shadowed world. Magnetic fields were once invisible, yet now they are mapped with exquisite detail. What other forces wait their turn? What other threads weave through the air, through your body, through the earth, still undetected? You sink a little deeper, held by that thought. The darkness grows softer as if inviting you inward. And in its center, you sense something even quieter, something not magnetic but gravitational, a field more subtle still, bending space itself so gently you never feel its touch. You drift into an even deeper quiet, where sound becomes a memory and weight becomes a suggestion. In this space, you sense something softer than magnetism, older than light, more patient than time itself. Gravity. A word you've always known, yet a force you've never truly felt, not in its purest, gentlest form. You feel its presence every moment, but only as a background certainty, a quiet pull that keeps your body grounded. Tonight, you move closer to its edges, where gravity whispers rather than commands. Gravity is often described as a pull, as though the earth tugs downward on everything resting above it. But in truth, gravity is a shaping, the bending of space itself. Massive objects carve dimples into the fabric of the universe, and smaller objects follow the curves. You fall not because the earth pulls you, but because the ground rises to meet you through curved space. You walk, and your path is guided by the shape of the world beneath you. In the darkness of this chapter, you imagine that fabric. A smooth sheet stretching into stillness, curving gently downward where earth sits. You picture yourself resting on that curve, feeling its guidance. Gravity isn't a command, it's a soft slope, a suggestion, a quiet invitation to move along its lines. Quantum sensors learn to hear that invitation. They are among the most delicate instruments humans have ever made. At their heart lie atoms drifting, falling, floating, responding to gravity's touch with the tiniest motion. What you feel as a simple downward pull becomes, to these atoms, a world of differences. A change in altitude so small you wouldn't notice it, a shift in density hidden beneath the soil, a passing gravitational wave stretching space by less than the width of a single proton, all these movements register in the atom's graceful descent. You breathe gently, imagining one of these atoms. Picture it suspended inside a chamber, cooled until it barely moves. Then imagine releasing it. In that moment, the atom enters a kind of free fall, a condition physicists call ballistic motion. As it falls, the atom accumulates information about gravity. Not through sight or sound, but through phase, a quantum wave measuring its own journey through curved space. This is the essence of atom interferometry, one of the most refined tools in quantum sensing. Atoms are split into two paths, like a whisper split into two echoes. One path rises slightly, the other sinks. When the paths are brought back together, the atoms interfere, creating a pattern. That pattern reveals how gravity differed between the two paths. The slightest variation, from a mass buried underground, from water flowing beneath soil, from a passing seismic ripple, reshapes the interference. You imagine these atoms drifting like dust motes in a sunbeam, except they float without light, without air, without warmth, suspended in a perfect quiet where only gravity speaks. Their motion becomes a poem written by the Earth's subtle pull. You rest in that image, feeling your own body as part of this gravitational landscape. Your bones are shaped by Earth's steady embrace. Your balance adjusts unconsciously to the planet's curvature. You live within gravity as a fish lives within water, never noticing the medium that holds you. Quantum sensors, though, notice everything. They measure gravity gradients, how gravity changes from one point to another. These gradients reveal the movement of groundwater, helping scientists track aquifers and droughts. They map the density of Earth's crust, showing where minerals hide or where voids might collapse. They detect slow deformations in landmasses, offering early warnings before earthquakes. The atoms inside these sensors become explorers, traveling distances too small for your eyes to see, yet gathering information that shapes entire continents worth of understanding. In your stillness now, you imagine an atom falling through a chamber. It begins its journey with no weight, as though floating in emptiness. Then gravity begins to act softly, steadily, ever present. The atom's path curves, its wave function stretches, and the sensor reads these changes like ink settling on a page. You can almost feel the sensation of falling, the brief moment when the ground slips away and the world becomes weightless. Quantum sensors live inside that moment constantly, capturing the truth hidden in the transitions between support and surrender. You drift with the thought that gravity is not only around you but within you. Every particle in your body exerts its own gravitational pull. Infinitesimal, yes, but real. You are part of the fabric, shaping it just as it shapes you. Each of your breaths creates the tiniest ripple in space-time. You are not separate from gravity, you are woven into its structure. This interconnectedness becomes even clearer when you consider gravitational waves, ripples produced when massive objects like black holes or neutron stars collide. These waves stretch and compress space as they travel across the universe, altering distances by unimaginable smallness. You would never feel them. Your body is too large, your senses too coarse. Yet quantum sensors someday may. Interferometers like LIGO already detect these waves by watching laser beams shift as mirrors move by a fraction of a fraction of a fraction of a proton. But future sensors built from ultra-cold atoms could drift freely in space, responding directly to the waves stretching of space. Instead of watching mirrors, they would become the mirrors, tiny, perfect, floating reflectors of spacetime's passing breath. You imagine yourself standing in the quiet of the cosmos, watching a distant ripple fold through the void. It reaches you not as noise but as motion, a motion so small it seems more like the memory of movement than movement itself. And yet it carries stories from billions of years ago, stories of massive stars spiraling inward, bending the universe around them. Quantum sensors offer a way to listen to those stories. You breathe softly, letting that idea settle into your chest. The universe is not silent. It hums with gravitational music, vibrations traveling endlessly through space. You simply need instruments quiet enough to hear them. Earth-bound quantum gravimeters already hold such quiet. They can sense passing trucks on highways kilometers away. They can detect the movement of lava beneath volcanoes. They can reveal the shifting of tectonic plates with precision beyond any classical tool. These sensors are not merely devices, they are extensions of the Earth's own sensitivity, a way of feeling what lies underfoot without touching it. You consider how the ground beneath you is never still. The planet swells as tides move. It subtly warps with temperature. It breathes water in and out of its soil. Gravity shifts with all of it, flowing like a slow tide through every point on the surface. Quantum sensors read that tide. And perhaps, you wonder, your own body does too. Your inner ear senses acceleration. Your muscles adjust automatically to balance. Your heartbeat changes rhythm when you lie down or stand up. You are a gravitationally responsive being, shaped by invisible curves. In the deep quiet of this moment, you let gravity become a comfort. A steady hand. A gentle guide. You feel its constancy as a kind of tenderness, holding you in place, promising that the world will not drift away while you sleep. You sense, too, that gravity is not the final frontier of sensitivity. Something remains beyond it, a realm not of force, but of light. Light that carries information across impossible distances. Light that can be squeezed, stretched, refined into something even more precise. Your breath softens. Your awareness narrows into a quiet question. If atoms can sense gravity by falling, What might they reveal when they begin listening to the faintest flickers of light? You rest again at the quiet threshold of awareness, drifting between thought and stillness, as the world of quantum sensing opens a new doorway. This chapter leads you into the secret life of atomic time, the way atoms keep rhythm, the way their steady whisper shapes navigation, communication, and the subtle illumination of physical truth. You settle deeper into your breath as your mind steps gently into this unfolding landscape. Time arrives to you in pulses, the rise and fall of your breath, the warmth in your chest, the slow settling of your limbs. But beneath the calm surface of your body, there is another rhythm at work, a truer rhythm, one woven into matter itself. And tonight, you turn toward that hidden beat, the quiet cosmic clock inside every atom. Imagine holding a single atom, perhaps of cesium or rubidium, not in your hand, but in the soft, inner space of your imagination. Picture it floating in darkness, no larger than a shimmering point. It is not ticking the way a clock ticks. It is humming, resonating, vibrating at a frequency so steady that even the universe has difficulty matching its precision. That hum, that unchanging, unwavering vibration is the essence of atomic timekeeping. And you breathe out, feeling how this idea softens as it settles inside you. That time, at its most precise, is simply a rhythm the universe refuses to disrupt. Quantum sensors use these rhythms, these atomic oscillations, to measure time with exquisite clarity. They transform atoms into clocks so steady they drift just a second every 100 million years. And while you're lying here, slowly unwinding from your day, it becomes comforting to think that somewhere, deep inside every atom of your body, there is also a quiet motion, a resonance always unfolding. Atomic clocks operate by listening for a very specific transition inside the atom, much like listening for a single perfect note in a symphony. When the atom leaps between two energy levels, it emits a pulse, an unimaginably tiny whisper of electromagnetic energy. Sensors tune themselves to this whisper with devotion, adjusting themselves until they catch the note with perfect resonance. You can imagine it the way you might tune a musical instrument, a finger sliding across a string, listening for the tone that rings truest. A quantum sensor does the same thing, only it listens not with ears, but with carefully controlled lasers and magnetic fields that cradle the atoms in silence. Inside these delicate instruments, atoms float in vacuum chambers, untouched by air or sound or warmth. They are held in beams of light, suspended so they cannot touch anything that would disturb their natural rhythm. This stillness is essential. Anything that rubs against their perfect oscillation introduces noise, and quantum sensing thrives only in quiet. In this way, you see a reflection of yourself. When your day grows busy, when noise fills your mind, your thoughts scatter. But when stillness comes, when the world falls away, your inner rhythm returns. Quantum sensing grows only in the same kind of stillness you are allowing yourself right now. You breathe gently, and the idea deepens. Atomic clocks form the backbone of global navigation, not by marking hours or minutes, but by telling exquisitely accurate time that satellites use to triangulate location. Every direction you've ever taken with help from a digital map, every moment a device knows where it is, depends on atoms humming their precise and ancient rhythm. It is soothing to think that navigation, something so tied to movement, direction, and choice, is grounded in something so calm. Even more delicate are clocks built with optical transitions, where atoms vibrate not billions but quadrillions of times per second. The faster the rhythm, the more precise the clock. It's like comparing the slow swing of a pendulum to the fine trembling of a tuning fork. Both are rhythms, but one sings with far greater sensitivity. When you picture these optical clocks, imagine them as tiny lanterns of stability, beacons lighting the structure of time itself. You feel curiosity rise again, but this time it does not startle you awake. It blends with the breath, with the heaviness of your limbs, with the gentle quiet around you. You let the fascination soften, like watching ripples fade on water. Quantum sensors use these atomic clocks to anchor measurements of gravity, motion, and even the subtle drift of Earth's continents. Over time, the planet moves in slow, wide gestures, continents easing apart, oceans reshaping themselves, and atomic clocks bear witness to it all. This idea settles into you like a warm weight. That time, measured so faithfully, becomes a map of the world's deepest motions. As you drift further into the softness of this chapter, consider this: an atomic clock works only when the atoms are untouched, unhurried, unpressured. Their perfection comes from their freedom. And perhaps that reminds you of something human, the way your clearest thoughts come when you are not rushed, when you are allowed to be exactly where you are. You imagine the atoms inside the sensor now, arranged in a cloud of slow-moving particles. Lasers cool them not by temperature you can feel, but by removing their motion, slowing their dancing until they are nearly still. This laser cooling makes the atoms easier to observe. Cold atoms linger longer in the measurement region, giving sensors time to listen closely to their whispering oscillations. You breathe in, noticing how cooling and slowing have become part of your own experience right now. The parallels become soothing, not literal but metaphorical, like the way a gentle voice lulls you into rest. The atoms, in their stillness, begin to speak more clearly. Their oscillations become regular, reliable, consistent. The quantum sensor, like a patient listener, adjusts itself, aligning with the exact frequency at which the atoms shift energy levels. This alignment is the heartbeat of the atomic clock. One atom does not give enough stability. But many atoms, oscillating together, form a chorus, a collective signal stronger than any individual voice. And you sense something comforting in that too, the way unity creates clarity. As you sink deeper into this chapter, the scientific details blur into something more emotional, more reflective. You feel the steadiness of the atomic rhythm as if it were a quiet companion. You sense how these clocks, invisible, incorporeal, guide ships, track storms, synchronize networks, and help researchers listen for gravitational waves. Their precision reveals tiny wobbles in Earth's rotation, seasonal changes in groundwater beneath the soil, even the slow lift and sink of land after ancient glaciers melted away. Timekeepers reveal geology. Timekeepers reveal astronomy. Timekeepers reveal the breath of the planet itself. Everything becomes connected through rhythm. And that rhythm echoes faintly in you. Tonight, you rest in this shared frequency, the atoms outside you humming in the instruments of science, the atoms inside you humming with life. It feels comforting that you are not separate from this precision, only unaware of it in daily life. Your body moves through time with the same invisible regularity that atomic clocks measure and celebrate. Let yourself drift into that thought, that your body contains the same ordered chaos, the same subtle vibrations, the same ancient frequencies that define the universe's timing. And now, as the chapter begins to soften toward its close, you sense that atomic clocks are not just devices but metaphors, reminders that even the smallest components of existence carry rhythm and constancy. They remind you that stability is not always loud or dramatic, sometimes it is the quietest thing in the room. Your breath lengthens. Your awareness widens. And just as your mind begins to settle like gently falling dust, a new question rises. If atoms can mark time with such flawless precision, what might they reveal when time begins to stretch, warp, or bend? With that soft wonder lingering at the edge of your thoughts, you drift toward the next chapter where time does not simply pass, but curves. You settle deeper into the quiet, letting the room soften around you, as if the edges of the world blurred gently into dusk. Your breath evens out, slow and steady. You feel the weight of your body sink into rest. And in this settling, you enter a new chapter of sensing, one where time no longer stays straight, where light bends and stretches, and where quantum sensors learn to listen to the shape of the universe itself. Time, you have always felt, moves forward like a river, steady, patient, always in one direction. But in the deeper layers of physics, time behaves differently. It twists. It slows. It curves around massive objects. And tonight, you drift into that possibility with the ease of falling into warm water. Quantum sensors have learned to feel these bends in time. Not through imagination, but through the smallest interactions, the subtle changes in how atoms oscillate when gravity presses on them, the way light stretches when it climbs out of a gravitational well, the faint delays in the rhythms of highly precise clocks. As you breathe, you picture a clock, not a ticking clock, not a mechanical object, but an atomic rhythm like the one you explored in the last chapter. Only now, imagine placing one of these clocks at the base of a mountain and another at the summit. To you, they feel the same. To your senses, time seems equal everywhere. But the universe knows differently. The clock at the base feels slightly more gravity, and so its atomic rhythm slows ever so faintly. The clock at the summit runs just a little faster. The difference is unimaginably small, too tiny for your body to sense, but a quantum sensor can hear the difference the way a keen ear hears a slight shift in pitch. You breathe out, and the thought feels calming rather than confusing. Time is not rigid. Time is gentle, elastic, responsive. It yields to gravity like fabric sagging under weight. You imagine time as a soft cloth stretched across space, dipping wherever something massive rests: the Earth, the Sun, the black hole at the heart of the Milky Way. Quantum sensors, with their precision and patience, trace these dips and curves, letting scientists map gravity with unprecedented detail. In laboratories around the world, engineers create gravitational sensors using clouds of cold atoms cooled to near absolute stillness. These atoms are launched upward in tall vacuum towers, floating weightlessly before falling again. As they rise and fall, lasers split their matter waves, sending them along different paths like gentle ripples in a pond. When the waves reunite, they interfere, combining in patterns that encode the story of their journey. If gravity changes even slightly, the interference shifts. The sensor listens to this shift. It translates the whisper of falling atoms into measurements of gravitational curvature. This is called atom interferometry, but to you, it feels more like a kind of quiet choreography, atoms rising and falling in slow-motion arcs, revealing the shape of time as they dance. You relax your shoulders. You let your breath soften. This is not a lesson, it is a lullaby woven from physics. These sensors can detect groundwater moving beneath soil, magma swelling in volcanic chambers, and even the slow settling of mountains. They can listen to Earth breathe its expansions, its contractions, its hidden circulations. And just as every chapter has reminded you, the smallest things often reveal the largest truths. You imagine bending light now. Not violently, not dramatically, but softly, the way a stream bends around a curve in the land. Gravity pulls at light, subtly guiding its path, stretching its wavelength when it escapes a massive object. This stretching is called gravitational redshift, and you sense the meaning intuitively, not academically. When light climbs upward toward weaker gravity, it loses a little energy and lengthens into redder tones. When light sinks downward into stronger gravity, it shortens, grows bluer, more intense. A quantum sensor can feel the shift. It can measure how light's color changes as it moves through curved spacetime, revealing not just where gravity is strongest, but how spacetime itself is shaped. You feel steadiness in your breath as you imagine this, instruments that listen not to sound, but to the bending of light itself. You picture standing on Earth, with billions of photons streaming past you, all slightly altered by gravity, all carrying the imprint of the unseen architecture of the cosmos. It feels calming to think that even in darkness, information is flowing everywhere. Light is always telling a story. And sensors, like attentive readers, follow its message. Your awareness loosens. Your mind floats at the edges of the thought. Quantum sensors also stretch their sensitivity towards something even subtler, the faintest distortions of spacetime caused by distant events. Imagine two massive black holes spiraling toward each other, far beyond the galaxies you can name. As they merge, they send ripples through the fabric of space, gravitational waves. These waves arrive at Earth so gently that they change the length of an object by less than the width of a proton. Yet quantum sensing helps build detectors so refined, so stable, that they register those impossible tremors. The universe hums, and sensors listen. You let that idea rest warmly inside you, that great cosmic events echo quietly through your world, and that humans have built instruments delicate enough to follow those echoes. Deep underground, in quiet chambers shielded from noise, clocks measure the passing of time so precisely that they detect tremors from quakes on the opposite side of the world. In research labs, cold atoms drift without touch, revealing how gravity curves in tiny variations. In space, satellites equipped with precise clocks help monitor Earth's shifting mass distribution as ice melts, seas rise, winds reorganize the planet's balance. Every measurement begins with silence. Every discovery starts with stillness. You recognize that rhythm now. Each scientific concept arrives calm and unhurried, then settles like sediment in the water of your mind. You let the understanding sink without needing to grasp every detail. The emotional truth matters more than memorizing the physics, the truth that the universe is flexible, responsive, alive with structure. Time is not a rigid line. Gravity is not just a force but a shaping presence. Light is not just illumination but a messenger. And you, resting here, are part of that same space-time, curved, stretched, influenced by mass, by light, by movement. The physics that governs galaxies also governs the quiet inside your chest. As the chapter drifts toward its final breaths, you allow the ideas to dissolve into feeling. The softness of time bending. The elegance of light stretching. The gentle intelligence of sensors listening to the universe's hidden architecture. You sense that this chapter is not an ending but a deepening, a settling into the realization that the universe is not static. It bends and breathes. And quantum sensors help reveal the subtle ways it moves. Your breath becomes slower now, almost sleep-like. And just before the chapter fades fully, a final question rises, delicate as a drifting cloud. If quantum sensors can feel the bending of time itself, what might they uncover when they begin to sense motion not just in space, but in the very particles that compose you? You ease into stillness again, letting this final chapter arrive like the slow dimming of twilight. The journey you've taken through the unseen world has reshaped the way you breathe, the way you listen, the way you imagine what lies beneath the surface of things. And now, resting here, you begin to sense the shape of what comes next, a future built not from vast machines or towering discoveries, but from sensitivities so small that they slip between atoms, following nature's quietest cues. The future, you realize, is not loud. It is not rushed. It is subtle, attentive, and deeply curious. Quantum sensors grow from that curiosity, instruments that do not push the world to reveal itself but instead wait, calmly, for the world to speak in its own delicate way. And as you drift into this final exploration, you begin to see how these gentle tools will transform medicine, navigation, communication, and your understanding of your own body. You breathe in slowly, and the future opens like a soft horizon. You begin with medicine, where the smallest changes matter most. Imagine a sensor so sensitive that it can detect the faint magnetic fields produced by your heartbeat before the beat fully forms. Imagine mapping electrical signals in the brain without touching the scalp, tracing each neural whisper with clarity that current machines can only approximate. You picture doctors listening to your organs not with heavy machines, but with quiet, quantum-tuned detectors that feel the slightest shifts in chemistry. Magnetometers based on single atoms, nitrogen vacancy centers in diamond, or ultra-cold ensembles of spins, these are not technologies of distant centuries. They are forming now, gently, like stars emerging in early twilight. You imagine a sensor nestled near the surface of your skin, reading the magnetic signature of a single neuron firing, its signal faint but distinct. You sense the intimacy of it, a measurement not forced, not extracted, but received. Your breath deepens. You realize the body is full of signals that were always present, simply too soft to notice. Quantum sensing brings them forward, not for intrusion, but for understanding. In the stillness, you feel gratitude for the complexity inside you, every cell humming, every ion shifting, every neural wave rising and falling in quiet tides. The future of medicine becomes a future of listening. You drift now toward navigation, moving through oceans, through deserts, through city grids, through space itself. For centuries, humans have relied on stars, compasses, satellites. But quantum sensors offer something new, the ability to navigate by feeling Earth's gravity itself, tracing its slight variations as naturally as following a familiar path by touch. In quantum gravimeters, atoms tossed upward in vacuum chambers become tiny explorers, mapping the curvature of space-time beneath your feet. Each interference pattern, each ripple in the matter waves, becomes a signpost. You imagine a submarine gliding silently beneath the surface, guided not by radio signals or GPS, but by gravity's signature, a map that cannot be jammed, cannot be hidden, cannot be lost. You imagine spacecraft navigating by the gentle tug of celestial bodies, quantum clocks marking time so precisely that a single second never drifts across an entire human lifetime. Your mind rests in the simplicity of it, to move through the world by sensing what has always been there. No hurry, no noise, no urgency, just precision woven into quiet. Next, you feel drawn toward communication, a future where information travels in ways that protect its meaning with fundamental laws of physics. Quantum sensors and their cousins in quantum communication make eavesdropping impossible. A measurement changes what is measured. You sense the beauty in that, the universe itself insisting on honesty. Imagine networks built not of wires and signals alone, but of entangled states linking distant points. Imagine messages encoded in single photons, fragile but secure, linking cities, continents, perhaps someday planets. You rest in the thought that privacy and security, often so fragile in the modern world, may soon be guarded by phenomena woven into the fabric of the universe. The future becomes gentler when its foundations are unbreakable. The chapter moves on, and you follow, floating deeper into what smallness makes possible. You imagine sensors embedded in materials, quiet watchers that detect stress in bridges before cracks form, that track the health of ecosystems by sensing chemical traces in the air, that measure seismic shifts too subtle to classify as tremors. You imagine farmers guided by networks of soil sensors that listen to nutrient levels grain by grain. You imagine climate scientists tracing carbon dioxide not by region, but by swirling patterns in real time. You imagine cities tuned to their own rhythms, lighting, heating, travel patterns adjusting not by schedule, but by sensitivity. Every improvement emerges from paying attention,